one term, what do you call it? Monomial. If you have two terms, you call it binomial. Three terms is, and more than three terms is polynomial, right? So we can classify by the number of terms. Really, we say classify. I mean, it's just that we're going to be using these words like vocabulary. I mean, it's just something you got to understand what we talk about if we say trinomial, right? And then we also classify by degree, right? And what does degree mean for a polynomial? The highest degree term, right, determines the degree of the polynomial. Okay, so what if the highest degree term is x to the first? Linear. What if it's 2, 3, cubic, 4, 5, quintic? Okay, and that's all the homework was on. But we spent most of the class working with the calculator, right? How do we use the calculator to model data, scatter plots, right? So let's go back over that. Especially if you weren't here, you should have your calculator out and be doing this, right? So how is it that we enter data into the calculator? Right? So the stat button is right here, right? You hit stat, and then edit is the first column, right, at the top of the screen. So you hit enter, and then underneath the L1, you put the X values. So this would be the X values in a list, right? And then underneath the L2, you put the Y values, right, in a list. That's how you enter the data, right? How is it that you can look at the data so that you can decide what kind of function you should use to model it? Right? You got to turn on the plotting of points, which your calculators, because they've been used for this all day today, maybe are already turned on for this. But if they're not, you go to stat plot. Where's stat plot? Yeah, above the y equals, so you've got to access it by hitting the second button and then the y equals. And then when you do that, this should say on. If it doesn't say on, then you have to hit 1 and then hit enter so that it stays on the on, right? That turns on the plotting of points. Okay, then you want to go to those points, which might be right around the middle of the graph anyways. But if they're not anywhere near the middle of the graph, then you don't necessarily want to hit graph, you want to hit zoom 9. Zoom 9 is zoom stat, and it brings you right to the points that you put in, right? So zoom 9. And those are different points, right? That's what yours should look like, right? If you put in those points that I just gave you. Now, which one of our kinds of functions has a graph that's kind of similar to that? I mean, if you look at it, it looks like there's 1 turn, 2 turns, 3 turns in the data, and that's what a quartic does, right? It has up to 3 turns in a quartic. Right, so we make our decision. Okay, it looks like a quartic. How do we then make a quartic model? Okay, so then we go to the stat, arrow over to the calc, and there's our menu of all those polynomial functions. Right, at number 4 starts at linear, quadratic, cubic, quartic. So you're going to go to stat, calc, 7 for quartic. Right? And when you get, your screen is going to have about 5 lines, the bottom one of which says calculate. So you want to get down to the calculate, and when you do, you're going to get this. The standard form of a quartic function, and it's got A, B, C, D, and E is all the coefficients, and then it gives you the values for A, B, C, D, and E. So you plug in, and I rounded to 2 decimal places for all of those. Now, the other thing that I showed you guys was you could actually have the calculator put that, instead of having to, like if you wanted to load that at y equals so that you could see the graph, you could actually have the calculator do this. And you should try it because it's actually very convenient to do this. If you just went through that process with me, then go to y equals, right? And then hit the vars button, which is right here, V-A-R-S, right? And when you do that, the fifth option is statistics, right? We put everything under stats, so you want vars, stats, and then you arrow over to the EQ at the top of the window. And what you should see is that it says regression equation. That's the equation that you just made, right? So when you hit enter, it puts it onto your y equals, the first line under y equals. Okay, now hit graph and see what you see. You're not, okay? It should draw your quartic function in the middle of that data, right? Is it hitting all the points? No, but it's what you call the best fit, right? It's minimizing the error between the function and the actual data. Right? Now, what if you were asked the question like, what would be the value of this function for x equals 10? Right? Go to the table of values, right? Then just go to the second graph and look in your table of values where x equals 10. The y value is, it's right next to it, negative 35.07. Right? So if you use this to make your regression model and then you're asked to make a prediction, it's very convenient to have put that function on the y equals first line. So then you can look up all your answers just in the table of values. You don't, I mean, it would be much harder if I had to come into this thing here and put 10 there and there and there and there and then do all the calculations with all these decimals. Much easier if you let the calculator do it. And then also, the calculator didn't round off any of that stuff. It's got everything in there. Okay, try this one. Try to do the same thing with that one. Enter the data, stat edit, look at the scatter plot, and if you already turned on the plot, all you have to do is do zoom 9. You don't need to turn it on, it's already on. And decide what kind of model. Graph. Not yet. Who's got a graph? Points. So what shape do you think that has? Okay. So Morgan's saying it looks like it's cubic. How many think it looks cubic? You think that looks cubic? Cubic? Do you do it? Okay. So the data's in there good. I think you might have one of your points is off. No, that's pretty good. But you might want to like clear that line so you don't see the graph. That looks good. Good job. Did you put the data in? Yeah. Zoom 9. Remember, zoom 9 brings you to the point. Yeah. Okay, you good? You did. Okay, zoom 9. Zoom 9. Done. That's okay. Now it's zoom dash 9. So when you entered that in, it should have looked like, I guess, zoom 9. I think I still have those points. No, I don't have those in anymore. It looked kind of maybe cubic. When I made it up, I was trying to make it look kind of linear, but I put too much of a shape that looked cubic. Everybody saw that as being a cubic, right? But it should have, you could have drawn the cubic function right through those points. Okay. What's that?
I turned my power was on.
Okay, then turn it back on. You have to do everything for you here? Zoom 9. Yeah. Okay. So that's just reviewing what we did last class. We'll do it again, right? That's a pretty important thing to be able to do. And it's actually not that hard. In fact, we're going to use this again later on in a way that probably no other teacher would show you, but something I like to do. Okay, I guess I already started recording anyways, but so this section here is pretty important. In terms of the SOLs, it's pretty important. Used to be even more important. But when they changed the SOLs, they made this a little less important. Out of everything in this chapter, this is the one section that's probably the most important of all of them. And, you know, like I said, I'm not going to read through all these now, but we'll go over them in pretty good detail at the end, and you'll see. It'll all make pretty much sense to you, what we're doing. The first thing that we're asked to do is to talk about functions increasing and decreasing. Right. Okay, hurry up. Okay. By increasing, what you mean, a function is increasing when it's going up from left to right. Right. So this, which looks like a cubic function, looks like it's going up, so it's increasing, and then it's decreasing because it's going down from left to right. And then it's increasing again. Right? That's what we mean. What's actually increasing here? The y values are increasing. Right? Now, if I highlight this, there's a new toy. Right? This thing is increasing from here to here. And then it's increasing again from here to here. And because those have arrows on either end, it actually goes on forever. Right? It's decreasing in the middle from here to there. Now, what we're asked to do is to give the intervals where it's increasing or decreasing. Right? By intervals, you mean intervals of x. Okay? So where is this thing decreasing, right? That orange piece of the graph starts at what value of x? And where does it end? 1. So you would say that it's decreasing from between -1 and 1. Now, how can I write that? In chapter 1, we did 3-part inequalities, right? 3-part inequality would say -1 is less than x is less than 1. Okay, so in between -1 on the left and 1 on the right, this thing is going down. It's decreasing. Right? Now, in order to say the interval where it's decreasing, right, that interval ends at -1, but it goes on forever to the left because that arrow goes on forever to the left. So the way you would write it, you would say that it's increasing for x less than -1. Right? That means for all the x's less than -1, that thing is increasing. How would I write the interval from here to the right? X greater than 1. Right? X greater than 1. Okay, how about this one? This one is increasing, looks like, from here to here. And it's increasing here up, and that goes on forever. And then this one is going down. It looks like a mess, but that's okay. So how are we going to name these intervals? How about this interval of decreasing? I'll put it at the top. It's decreasing until it gets to this point. How do I name it? Decreasing for, come on, look at, how do we name it over here? X less than -3, right? 1, 2, 3. So you say x less than -3, right? How am I going to call this interval here? You got it? I think it's 4. 1, 2, 3, 4. So 0 is less than x is less than 4. X equals 0. Right? Remember, you're not talking. So what about this interval here? How do I name that interval of increasing? You got it. What'd you say? 0. Right? In between -3 and 0. Okay, how about this interval of increasing? How about x is greater than 4? So notice that when you say here x is greater than 4, and here you say x is decreasing for x is less than 4, what's going on is 4. Is it increasing or decreasing? It's not doing either one, right? Right at that point, it's not increasing or decreasing. What is the straight line doing over here? It's what now? The way you would say that is you would say it's increasing for all real numbers. Okay? So you say increasing. Either you go like this, right? Increasing for all reals. Or another way that we write that, and this is kind of a little more pre-calculus-y, right? But that is, you would say it's increasing from -infinity on the left to +infinity on the right. So all this from the extreme left to the extreme right, that's another way of saying all real numbers. And you could use that same kind of notation up here, right? I could call that interval right there -1 to 1. Using interval notation, you could do that. Okay, so how about this one? A parabola is increasing and then it's decreasing. This one is increasing and then it's decreasing. So let's see, it's increasing over here. It's decreasing over here. So how can I name these intervals? What is this interval of increasing? Where does it stop increasing? At 2. So I can say it's increasing for x is less than 2, and it's decreasing for x is greater than 2. Okay. So that's what they mean by intervals of increasing and decreasing. Usually the place where we make the most mistakes with that is we give the y values instead of the x values. Like in this one here, you say it's decreasing, and you're going to want to say -2, but that's the y value, right? We don't give the y values; we only give the x. Okay. The next thing is this thing that they call end behavior, and end behavior is something that is kind of new to the Algebra 2 curriculum, and I'm not even sure that this book has it. Kind of like we're going to see it in the SOLs, but it is what it is. In the previous homework assignment, the one we just went over, they did have some some end behavior kind of stuff. And this is the way that they did it. Like for this one here, if you had to describe the end behavior, which means what is the graph doing on the left and what is the graph doing on the right, the way the book called it, they said down and up. That was it. This one would be up and up. It's like they're going to give it in order. What's it doing on the left? What's it doing on the right? And what about this one? On the left, down, and on the right, up. And on this one, on the left, down, on the right, down. The pre-calculus does it like this. They say falls to the left, rises to the right. That's the way they would say the same thing. I think that on the SOL, if I've seen that on our Algebra 2 SOL, and actually I think that we did see it on the one release test, that they did something more like this. They said, as x approaches infinity, right, meaning going to the right end of the graph, then you would say that y is approaching positive infinity, because it's going up like that forever. Like over here, you would say as x is approaching positive infinity, the y's are approaching negative infinity. So I can't guarantee the way you're going to see that. In fact, there is some confusion with end behavior being something that we study in a few chapters from now too. But that is end behavior, at least the way it's being dealt with now. The last thing is zeros, right? The zeros of the function are the x-intercepts. Okay, they are the x-intercepts. So what kind of function is this first one? It's probably cubic, right? It isn't drawn very well, but it's probably a cubic. How many zeros or x-intercepts do you see? 1, 2, 3. And that's the most zeros that you can get from a cubic, right? It's whatever is the degree, that's the most zeros that you can get. How many zeros do you see on this one? Quartic. Yeah, you actually see 4, right? It could have, you actually see 3. It could have 4, but it doesn't. It actually only has 3. 1, 2, 3. And how about a first degree polynomial, which is linear, can only have 1, and it has 1. Right? There's only one linear function that doesn't have a 0. What is it? Could you say again? A horizontal line. Y equals something. Okay, so now most of what we do in the lesson today has to do with zeros. So let's move on. Actually, I meant to delete that. Okay, Josh, you want to stay after? Okay, you're gonna. Got to grow up. You understand? Okay, first, what is the factored form of that polynomial? Now, it's a cubic. Understand that so far, we didn't really study any factoring of cubics. And out of the 4 or 5 kinds of factoring that we did talk about, right, there's only one that might apply here. Certainly nothing that talks about quadratics would work, right? So difference of squares, simple or not simple quadratics, they wouldn't work. But which is the one method that would? The GCF, right? So if you look at that there, is there a common factor in all of those? X, right? So you take an X from every term. And then when you look in the parentheses, that is a quadratic, and you can factor it. How does it factor? Come on. 3 and 5, except one's got to be positive and one's got to be negative. -5. Okay, so that's the factored form. That's the first example in the book. I might have another one that comes after this. Try to do the same thing on that. Are you still looking at that? Okay, hurry up. Try to do the same thing on that. Factor it. We don't seriously need a calculator for this, do we? Right? You factor out the common factor, and then what's inside? How does that factor? Yeah. X times x minus 4 times x plus 3. Okay. Sure. Okay. Find the zeros. Now, technically, what you mean by a 0 is the value of x that makes y equal 0. right? 0. The value of x for which y equals 0. So if you're given a function, y equals, you're going to substitute y equals 0. And then when you've got your polynomial in factored form, that means you can use the zero product property. You know, even we did this in the chapter which was quadratics, which meant you could have 2 factors. But now we've got 3 factors, still the same thing. If you multiply a bunch of things together and the product equals 0, it must be that one of the factors equals 0. So what values of x are going to make each one of these factors equal 0? -2, 1, and 3, right? If you have to, you can make an equation, x plus 2 equals 0, and solve. But you should be able to see a 1x plus or minus a number just by inspection, right? -2 plus 2, 0. So the answers are -2, 1, and 3. What is the degree of this polynomial? You know, in the factored form, you don't see that highest power term. But imagine if we multiplied all these together, the first term would be x times x times x, x to the third. So 3 zeros is kind of what you expect. Okay. Now, again, when we say a zero is the value of x where y equals 0. Well, where does y equal 0 on a graph? It's on the x-axis, right? Y, which is telling you where you are above or below the middle. Well, if you're right in the middle, then y equals 0. That's why the x-intercepts are the zeros, right? There, and there, and there. Right? And does that look right? Okay, -2, 1, and 3, those look correct. So now we have to notice the relationship between, these are called zeros, right? These are called linear factors, right? So notice the relationship. Start with the 1. If 1 is the 0, the linear factor is x minus 1. If 3 is the 0, then the linear factor is x minus 3. In general, if you have a 0, then x minus the 0 is the linear factor. Okay, well, how does that work for a 0 of -2? Yeah, I mean, x plus 2 is x minus -2. Right? So it works. So these linear factors right, are equal to x minus the 0, whatever it is. We good? Shiza? Okay. Okay, so start here. So if my zeros are -4, -1, and 2, what are my factors? Mark? No. Linear factors. X plus 4, x plus 1, x minus 2. Okay, then what would the function be in factored form? Y equals x plus 4, x plus 1, x minus 2. Right? The factored form of the function. good? Trevor? Lee? Okay, what if you have the factors? How can I determine the zeros? Yeah. Yeah. Good. Okay, and then what would the function be? Okay, good. X plus 5, x plus 3, x minus 6. It's not too hard, is it? Okay, try this one. Turn those zeros into factors and then the factors into a function. So do it. What are the factors? X plus 0.
Wouldn't that just be 0?
Well, first of all, why wouldn't, if you were going to say, why wouldn't you say x minus 0? But, you know, if you start out by doing the x minus 0, because we said always do x minus, right? You wouldn't leave it like that. You're going to make that x, right? Minus 0 doesn't change it, so you're just going to write x times x minus 9 times x minus 10. But that brings up a really important point, because we miss this one all the time, that when you have a factor of x, that means the 0 is 0. Okay, we miss that one all the time. Okay, so now the function is y equals x times x minus 9 times x minus 10. Okay. Now, what if you're given the graph? How can we find the zeros, John? Okay, what are the x-intercepts here? -2 and 0 and 2, right? So here's our zeros, -2, 0, and 2. So if you have a graph, then find the zeros and then turn them into factors. And what are the factors this time? Right. X plus 2 times x minus 2. Most of the time, you'd put the x, the standalone x, at the beginning. Do you have to? No. Commutative property says you really don't have to. But normally, you wouldn't see the x like buried in the middle of the two binomials. And then, so what does that make the function? Y equals x times x plus 2 times x minus 2. It's too easy, right? Okay, so do this one. Turn those into zeros and factors and functions. You want to stay after? Do I really have to say that? What are the zeros? -3 and 2, right? So what are the factors? X plus 3 and x minus 2. No problem there. What is the function? X plus 3 times x minus 2. There is a slight problem here. Okay, if I foiled that to put it into standard form, right, then what would the first term be? X squared, positive x squared. But when a quadratic has a positive first term, it opens up. That thing doesn't open up, right? So we would have to have a minus in front. The zeros are still the same. But it opens down, so we put a leading negative. piece of cake. Okay, now, this is one of the problems that we had at the beginning where we had to factor it, right? Here's how you could factor this without factoring it, by just doing the things that we were already doing, right? Put that standard form of a polynomial in the calculator and see what you see. X to the third. All right, make sure you get out of the exponent, right arrow. Then you got minus x squared minus 12x. Right, and you look at the graph, zoom 6. And do you see the zeros? Okay, and what does it look like they are? Negative 3, 0, and 4. So here it's negative 3, 0, and 4. What are the factors? X plus 3 times x minus 4 times x. Okay. Well, that is, when we factor that expression, that's what we got. Right? So we came up with the factored form of that expression without factoring it by looking at the graph, finding the zeros, and making our linear factors. Right? Now, I could still write this function, x times x plus 3 times x minus 4. So that those two are equal. One of them is standard form, one of them is factored form. That's it. So actually, if you know how to do this stuff, it can help you when you have to factor things. I think I'm going to skip the next slide because you guys don't need it. Okay, now, here's the typical kind of problem that you get in this stuff, right? Which is, it says, write the polynomial function given the zeros, right? And they're giving us the zeros at the end, negative 2, 2, and 3. And they're actually telling us it's going to be a cubic, which makes sense because 3 zeros, cubic, that kind of makes sense, right? So how are we going to do that? We have to turn these zeros into factors first. What are the factors? X plus 2 times x minus 2 times x minus 3. And then you have to multiply, right? Now, you can't multiply all three together at one time. You're going to have to pick two of them and FOIL, and then you'll multiply that by what's left. So let me pick these two as the first two and FOIL. X squared minus 3x minus 2x plus 6, which is x squared minus 5x plus 6. Okay, and now we still have to multiply by the x plus 2. Right, so the first step was a FOIL, and we're familiar with that. This next step is not really a FOIL because FOIL is for binomial times binomial. This is binomial times a trinomial. How many terms are we going to make when we multiply 2 terms times 3 terms? 6 terms, right? And then just like FOIL, there will be some combining of like terms to do. Now, how you do this is up to you. You don't have to do the way I'm going to show you. When I was your age, I didn't have any particular method. I just started multiplying. X times everything there, 2 times everything there, combine like terms. But this is a way that a lot of kids like to use, and that is make yourself a little grid. And I made it a 2 by 3 in that I'm going to put this x plus 2 on the left, and I'm going to put the x squared minus 5x plus 6 on the top. And then I'm going to fill in the grid by multiplying what's on the left and what's on the top to get what goes in the cell, right? So this first cell here will be x times x squared, which is x cubed. Right? And this one will be x times negative 5x, negative 5x squared. And then x times 6, 6x. And 2 times x squared, 2x squared. And 2 times negative 5x, negative 10x. And 2 times 6, 12. Okay, so we made 6 terms, right? But some of them are like terms, so you're going to have to combine them, right? There's x squared terms here, and there's x terms here. So as I write this out, our answer is x to the third, 2x squared minus 5x squared, negative 3x squared, negative 10x plus 6x, okay, minus 4x, and then we still have our plus 12. Most of these problems say write it in standard form. They never say write it in factored form. They expect you're going to make your factors and then multiply. And this doesn't go away. They get more complicated in the next class. It involves imaginary numbers and conjugates and all kinds of stuff. Okay, but here's a way you can do this same thing using the calculator and the modeling stuff that we were doing at the beginning of class and last class. Okay, first, how many points does it take to determine a line? 2 points, right? Meaning, if you have 2 points, there is only one line that can connect those 2 points. There's only one straight line that can connect those 2 points. Okay, well, it turns out for a quadratic, it's 3 points. If you have 3 points, there's only one quadratic function that could go through exactly those 3 points, right? And for a cubic, you need 4 points. 1, 2, 3, 4. So you see the pattern here? Whatever is the degree of the function, you need one more than that, points. Right? So how many do you think we're going to need for a quadric? 5 points, right? And the truth is, they don't have to be well spaced out like I just showed them. It could be 5 points that are like right like that. As long as they're not on the same vertical line, which would make it not a function, it'll work. So understanding that, we're going to answer the same problem by doing a modeling, right? By doing something with our stat edit and that. So the first step would be make your linear factors, right? Which we already did in the last problem. It was x plus 2 times x minus 2 times x minus 3, and you put them on the y equals, right? In the calculator, go to y equals and write in factored form, write x plus 2 times x minus 2 times x minus 3. Once you have that in the calculator, go to the table of values, right? Second graph, right? And I've already done that here. That's what this is right here. Hit second graph, and you're going to get a table of values. It should look pretty much like this. Maybe you've got a scroll so that you have 0 on the top, but you should have something like that, right? Now remember, we're trying to make a cubic polynomial. How many points do we need for a cubic to find the one cubic polynomial that goes through? You need 4 points, right? So once you've put the function in factored form, you've gone to your table of values, take any 4 points, right? Any of these 4 points, or scroll up or down, whatever, just take 4 points from the table of values. And maybe you want to write them to the side or something like that. Then go to your stat edit and put those 4 points in your list 1 and your list 2. So I picked the first 4 points. Okay. Once you've got 4 points in there, then you're going to make the cubic model, right, by going stat, calc, and then 6 is the option for cubic. And you should see a screen that looks like that. Lee? You raising a hand? Okay. Now, there's my standard form of a cubic, and then if I fill in for A, B, C, and D, I get exactly what we got on the last slide. see that? I mean, it could actually be even easier than that. But I think this is like the most general procedure if you wanted to do it like this. Another way you could do it is you actually have 3 points right here because these are zeros. You know you've got negative 2, 0, 2, 0, and 3, 0, right? And then for your y-intercept will be, remember, if we make our linear factors of x plus 2 times x minus 2 times x minus 3, the y-intercept will be the 2 times negative 2 times negative 3. So what is that? 6, 12. So the y-intercept will be 0, 12. So without ever even having to put it in the calculator, I know the 4 points that I'm going to use. Now, when does that not work? That doesn't work if one of your zeros is 0, because then an x and a y-intercept are actually the same point because it's going through the origin. But it's easier just to say, put it in factored form, grab as many points as you need for that particular polynomial function, and then put them under stat edit, make your model. Now, is that a best fit model? No, it's not a best fit. It's the only cubic function that can go through all of those points, and it will go exactly through those points. Remember, you get the best fit when you've got more points than you need to make that kind of function. So try to do the same thing with that. Remember, turn those zeros into linear factors, and then put those linear factors on y equals. And then it's a cubic function, so again, you're going to need 4 points. Yeah. I don't know what you're talking about. Okay. So let's go for this one. What are your linear factors? Okay, put it in there. X minus, parentheses, x minus 3, parentheses, parentheses, x minus 3 again, parentheses, parentheses, x plus 3. Okay, now go to your table, second table, take 4 points. Okay. Who's got a function for me? Natalie? Let me see. Yes. So this one Natalie's got. X to the third minus 3x squared minus 9x plus 27? Yeah, plus 27. Okay. So, I mean, this is definitely an extra thing. You're not going to find this in the book. I'm sure no other teacher showed anybody how to do that. But to me, that's just a pretty neat thing. If you know how to do the modeling stuff, then why not use it? And so how high of a polynomial could we deal with? Well, we go up to quartic. We can make quartic models. So as long as you get 5 points, then you can do it. Now, this is a particular kind of problem here because actually it has a repeated 0, right? It's got 3 twice, which brings us to the last point. So we could have written this thing in factored form like this. X minus 3 squared times x plus 3. Okay, look at the graph of that function. Okay, there's your 2 zeros, but they definitely don't look the same, right? At negative 3, the graph goes right through the 0 and onto the other side. But at positive 3, it touches the 0 and it goes back in the same direction. Okay, that's what you expect happens when your 0 is coming from a factor which is being raised to an even power. Okay, and the reason is because take for example at negative 3, right? If I go to negative 4 plus 3 is negative 1, right? It's a negative, so that factor is negative. If I go to positive or negative 2, then negative 2 plus 3 is positive 1. So on either side of the 0, that factor changes sign, right? But if you go to the 3, because it's being squared, right? If I look at what's the value of that factor at x equals 2, 2 minus 3, negative 1. But then you square it, and it's positive 1, right? What is the value at 4? 4 minus 3 is positive 1, and when you square it, it's still positive 1. So this factor is not going to change sign on either side of the 0. It's going to have the same sign because that is an even number. So this is what you expect when the factor is being raised to an odd power. This is what you expect when the factor is being raised to an even power. Okay. When a factor is being raised to a power higher than 1, then that exponent is the multiplicity of the factor or the 0, right? So when 0 comes from a factor with exponents greater than 1, right? It's called multiplicity. So just, if you looked at that function, if you were given it as is and told, what are the zeros? You would say that the zeros are 3, and then you would have to give a comment, multiplicity 2, to make it clear that that actually occurs twice. It's not there just once, it's twice. Usually I write it like this, mult 2, and then negative 3. I mean, you got to make it clear that the multiplicity comment doesn't go with all the zeros. It goes with the 1 0 that's being raised to a higher power. Okay? And last, so what are the zeros that you see in this graph, given now what we know about the characteristics of these zeros? So what is this? Negative 3? Multiplicity 2, right? And then that is 2, just once. Well, what is the shape of this graph? We could pretty well say it's going to be cubic. Somebody got a cell phone? It's going to be cubic, so how many zeros could it have? It could have 3, right? So, I mean, this could be there twice and there could be once. Remember, really what it means is that's there an odd number of times and that's there an even number of times. But there's no way that it could be more than 2 and 1 because you can only have 3, right? So we would say the zeros are negative 3, and you could say it with a comment, mult 2 and 2. And the factors would be x plus 3 squared x minus 2. And the function would be y equals x plus 3 squared x minus 2. Clear as mud? Yeah. So now let's read through these and see if we didn't touch on most of everything here. Okay, given the graph of a function, identify intervals on which the function is increasing and decreasing. Intervals of x, remember, x. Don't give y values. Identify domain and range, we didn't actually do that. Zeros and intercepts, we did do. We did it actually algebraically. We found the zeros algebraically when we factored it, and we also did them by graph. Describe the relationship among solutions of an equation, zeros of a function, x-intercepts of a graph, and factors of a polynomial expression. Okay. Define a polynomial given its zeros. Determine a factored form of a polynomial expression from the x-intercepts of the graph. We did that too. And then for a function, identify the zeros of multiplicity greater than 1 and describe the effect of those zeros on the graph. That's it. Okay. That's a lot. Like I say, if you knew all of that before 2009 SOL, you'd get through the SOL with just knowing that stuff right there. But now they put a lot more stuff that comes from the next chapter and then the one after that. And that's what brings us down. Okay. So that is the homework. No, do them all. What's the clue? I mean, each interval's got an odd and an even number, so obviously it includes odds and evens.